This paper investigates the Gevrey regularity of solutions to a class of inhomogeneous nonlinear moment partial differential equations, where the inhomogeneity is sigma Gevrey with respect to the time variable t. The authors generalize previous results on nonlinear partial differential equations and linear moment differential equations, focusing on equations of the form 1, where b kappa, m0, 2, p, and lambda are polynomials with analytic coefficients on a polydisk d rho 0, rho 1, rho n. The inhomogeneity RFPT xq is a formal power series with respect to t, and the initial data phi jpxq are analytic on d rho 1, rho n. The authors demonstrate that the Gevrey regularity of the formal solution rupt xq of eq 1 depends on both the Gevrey regularity of the inhomogeneity RFPT xq and the structure of the equation itself, defined by the nonlinear operator b kappa, m0, 2. To achieve this, the authors employ methods from previous studies on linear moment differential equations and nonlinear partial differential equations. They analyze the geometric structure of the Newton polygon associated with the equation, which plays a crucial role in determining the Gevrey regularity of the solution. The paper contributes to the understanding of the relationship between the Gevrey regularity of the inhomogeneity and the structure of the equation, providing insights into the nature of the solutions for these types of equations. This research has implications for various fields within mathematics and physics, including the study of singularities and the behavior of solutions near them, as well as the development of new methods for solving such equations. This research paper investigates Gevrey series solutions to a specific type of partial differential equation, examining the relationship between the Gevrey order of the inhomogeneity and the Gevrey order of the formal solution. A crucial operator, increment kappa, p, is introduced, which determines the Gevrey order of the solution. The paper is structured into 6 sections. Section 2 reviews definitions of moment functions and moment differential operators, along with their basic properties, including regular moment functions. Section 3 defines and explores the properties of Gevrey formal power series. The notion of modified Nagumo norms is introduced in Section 4, generalizing previous results. Section 5 formally introduces the main problem, defining the Newton polygon for the considered equation and demonstrating that the problem is formally well posed. The main result, presented in Theorem 5.7, establishes a connection between the critical value of the equation, the Gevrey order of the inhomogeneity, and the Gevrey order of its formal solution. Several examples illustrate this result. The proof of Theorem 5.7 is presented in Section 6, employing modified Nagumo norms and the majorant method to prove the first point, and a detailed example to prove the second point. Throughout the paper, notations are defined for sets of non-negative integers, positive integers, non-negative real numbers, and positive real numbers, as well as operations on these sets, such as scalar multiplication and the scalar product. Notations for moment differential operators, polydisks in complex space, the gamma function, and psi function are also introduced. The Gevrey regularity for inhomogeneous nonlinear moment PDEs is discussed, introducing the concept of a sector with an opening angle alpha and a radius r, denoted as SDP alpha, RQ. Kernel functions are defined as holomorphic on a specific sector, exponentially flat at infinity, and satisfying certain integrability conditions. Moment functions are introduced as the Mellin transform of kernel functions. A moment sequence is defined as a sequence of moments obtained from a moment function, highlighting the novel ideas and significant findings in this section. The definition of a kernel function of order S is introduced as a function of the form EPTQ, where EPTQ is a kernel function of order S. POD2 is defined in definition 2.1. The corresponding moment function M is defined by the same formula. Example 2.5 provides a classical example of kernel functions and their moment function, widely used in the classical theory of K-summability. Proposition 2.6 discusses the properties of the moment function M, including its holomorphy, continuity, and positivity, along with an estimate for the kernel functions E and E. The concept of regular moment functions is introduced in definition 2.7, stating that a moment function m of order s is regular if there exist two positive constants a and a such that apj(1qs and mpjq are bounded by apj(1qs for every jpn. Example 2.8 shows that the moment function mp lambda q gamma p1(s lambda q is a regular moment function of order s. The page concludes with a discussion on Stirling's formula and its implications for the moment functions. The concept of moment differential operators or moment derivatives was first introduced by W. Balcer and M. Yoshino. A moment function m0 of order s0 is greater than or equal to 0 is defined as a formal power series in OPD rho 1, rho n QRRTSs, with m0, p lambda, equals gamma, 1 plus lambda. The moment derivative bm0, t of m0 with respect to t is also a formal power series in OPD rho 1, rho n QRRTSs, where bm0, t coincides with the standard derivation operator bt with respect to t when m0, p lambda, equals gamma, 1 plus lambda. This definition can be extended to analytic functions at the origin of Cn plus 1 through their representation as infinite series. The operators bm0, t and bmj, xj commute with each other, and bmj, xj commutes with bml. xl for j does not equal l. Proposition 2.10 states that if a, t, x, is an analytic function on d rho 1, rho n, and m0, m1, mn are regular moment functions of respective orders s0, s1, sn greater than 0, then for any i0, i1, n is greater than or equal to 0, the formal power series by 0 m0, t by 1 m1, x1. Bin mn, xna, t, x, also defines an analytic function on d rho 1, rho n. This result ensures that the application of moment derivatives does not reduce the domain of analyticity of the original function. The proof of the theorem on the convergence of a formal power series begins by defining the series and its parameters. It then establishes a set of inequalities, which are used to demonstrate the normal convergence of the series on a specific domain. The proof relies on the properties of moment functions and their regularity. The conclusion asserts that the series defines an analytic function on the specified domain, thus completing the demonstration. In the realm of inhomogeneous nonlinear moment partial differential equations, PDEs, Gevrey regularity is a pivotal concept. A formal power series is considered Gevrey of order sigma if it meets specific inequalities concerning its coefficients. The set of all such formal series, denoted by OPD rho 1, rho n QRRTSs sigma, forms a C-differential algebra with respect to standard algebraic operations and derivatives. This algebra also remains stable under moment derivatives when dealing with regular moment functions. The Gevrey order sigma serves as a measure of the growth rate of the coefficients in the series, with higher values indicating slower growth. The primary finding here is that these series are stable under both time and spatial derivatives, as well as moment derivatives, which is crucial for the analysis of inhomogeneous nonlinear moment PDEs. Modified Nagumo norms are introduced as a tool possessing properties similar to standard Nagumo norms. This is achieved by defining a formal power series and a majorant series. Specifically, for an analytic function on a polydisk, the modified Nagumo norm is defined in terms of the indices p alpha, r, and s. This norm is rooted in the classical concept of majorant series and is employed to analyze the stability of sets under moment derivatives. The definition of the modified Nagumo norm involves the power series and the majorant series. The power series is a formal series of the form sigma, Cj, Pj, where Cj are the Taylor coefficients of the analytic function, and Pj are positive real numbers. The majorant series, on the other hand, is a series of the form sigma Cjzj, where z is a complex variable. The indices p alpha, r, and s play a crucial role in the definition of the modified Nagumo norm. The index p alpha is a multi-index, r is a positive real number, and s is a real number. The norm is defined as the supremum of the majorant series over the polydisk, subject to certain conditions on the indices. The modified Nagumo norm is applied to analyze the stability of sets under moment derivatives. This involves studying the behavior of the norm under differentiation and integration. The norm's properties, such as its ability to characterize the stability of sets, are essential in understanding the behavior of analytic functions on polydisks. This novel approach provides a powerful tool for analyzing the stability of sets under moment derivatives, offering insights into the properties of analytic functions on polydisks. The Gevrey regularity for inhomogeneous nonlinear moment PDEs is a pivotal concept in mathematical physics. It involves the definition and properties of modified Nagumo norms, which are crucial for understanding the behavior of solutions to these equations. The modified Nagumo norms, denoted as F, alpha, R, S, are defined on the space OPD ρ 1, ρ n q. A key result in this context is proposition 4.4, which proves that F, alpha, R, S is indeed a norm on this space. This proof relies heavily on the concept of majorant series and the triangle inequality, demonstrating the norm's properties. The definition of modified Nagumo norms for alpha dp's 0, 1r presents some limitations and potential avenues for future work. Despite these challenges, the technical details presented here provide a clear and concise framework for understanding the Gevrey regularity in inhomogeneous nonlinear moment PDEs. This knowledge can be instrumental in advancing our comprehension of complex physical phenomena modeled by such equations. The refined version of the transcript for the explainer video is ready. It accurately summarizes the key findings and methodologies from page 10 of the research paper, focusing on lemmas 4.5 and 4.6, and proposition 4.7. The content is concise, technical, and professional, ensuring that the complexity of the original text is preserved while being easily understandable for expert researchers and stakeholders. Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs, is examined through the lens of modified Nagumo norms and their relationship with moment derivatives. A crucial proposition is established, providing an inequality involving modified Nagumo norms, which is essential for proving Gevrey regularity. This proposition relies on the assumption that the moment function is regular and exhibits specific growth rate properties. Notably, the assumption, d1 for all d equals 1, n, is necessary to ensure the validity of the inequality, and the proposition accommodates scenarios where either alpha or beta is 0. A corollary derived from this proposition reveals that, for alpha and beta within specific ranges, the modified Nagumo norms satisfy a particular relationship. Two results are presented to illustrate the action of moment derivatives on these norms. Proposition 4.10, adapted from a previous work, provides an estimate for the modified Nagumo norms when applied to a moment derivative. This estimate is dependent on the order of the moment function and the regularity of the moment function itself. The proof of this proposition leverages the regularity properties of the moment function to establish the desired inequality. The authors derive a series of inequalities and propositions connecting modified Nagumo norms to the Gevrey order of formal power series. Specifically, they establish an inequality involving the modified Nagumo norms, denoted by B, and parameters alpha, R, S, and lambda, which is derived from the definition of modified Nagumo norms and properties of moment functions. Corollary 4.11 assumes regularity of moment functions m1, mn and provides an upper bound for the modified Nagumo norm of a function f, bq, m, xf, in terms of parameters alpha, q, r, s, and lambda. The authors then link modified Nagumo norms to the Gevrey order of formal power series. Proposition 4.12 states that if a formal power series is sigma Gevrey, its coefficients satisfy an inequality involving modified Nagumo norms and parameters alpha, r, s, and sigma. Furthermore, proposition 4.13 provides an upper bound for the absolute value of a function f evaluated at a point x, f, x, in terms of the modified Nagumo norm of f and parameters alpha, r, and s. The authors employ mathematical concepts such as moment functions, modified Nagumo norms, and Gevrey order, and utilize techniques like the Cauchy formula to derive these inequalities and propositions. These results are crucial for establishing the connection between modified Nagumo norms and the Gevrey order of formal power series. On page 13, The authors provide a proof for the Gevrey regularity of inhomogeneous nonlinear moment PDEs. This proof is initiated by establishing an inequality for any alpha, which is then applied to find a majorant series for the function fp, x. The inequality, 7, and notation 4.1 are utilized, ensuring the restriction on epsilon. The proof concludes by demonstrating that the supremum of fp, x, over a specified domain is bounded by a specific expression involving lambda p alpha q and epsilon. This sets the stage for the main results, focusing on inhomogeneous nonlinear moment partial differential equations of the form 8. These equations are characterized by a positive integer kappa, a nonempty finite subset lambda, and specific definitions for b, q, and p. The polynomial p is expressed in the form of equation 9, where I is a nonempty finite subset of n, and lambda n is a nonempty finite subset of n tuples pi, q, rq, with v, q, r being a non-negative integer for every pi, q, rq in lambda n. The coefficients I, q, rp, t, x are polynomials in P, D, rho 0, rho 1, rho n, and I, q, rp, 0, x, equals 0 for every pi, q, rq in lambda n. According to proposition 5.1, equation 8 is formally well-posed, with its proof involving the Taylor series expansions of the coefficients I, q, rp, t, x, and the inhomogeneity rfpt, xq. The coefficients uj, pec of the formal solution rupt, xq are uniquely determined by the recursion formulae, 10, which incorporate the initial conditions uj, pec equals phi jpxq for j equals 0, kappa, 1. The recursion formulae, 10, are derived from the Taylor series expansions of I, q, rp, t, x, and rfpt, xq, and involve the coefficients c, q, r, j, npxq, defined in equation 11. Notably, the moment multinomial coefficient jj0, jr1 rnm0 is of the form jj0, jr1 rnm0 equals m0pj0q m0pj1q, m0pjr1 rnq. Importantly, the third sum in equation 10 vanishes when j less than v, q, r, and the term r1 rl, 1 in equation 11, is 0 when l equals 1, resulting in junior 1 rl, 1 equals j1. The paper discusses the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs. It highlights that all coefficients uj, pec are analytic on d rho 1, rho n due to the assumption of regular moment functions and proposition 2.10. The Newton polygon for the nonlinear operator increment kappa, p is defined, which is a convex hull of certain points in the plane. An assumption is made that for any npi and all pi, q, rq p lambda n, ni l, 1 rlv, q, ra kappa. The geometric structure of np increment kappa, pq is specified in proposition 5.4, showing that if S is empty, the moment Newton polygon np increment kappa, pq is reduced to the domain CP's 0 kappa, kappa q with no side having a positive slope. If S is non-empty, the moment Newton polygon has at least one side with a positive slope, with the smallest positive slope determined by the minimum value of the ratio of the first and second components of the points defining the polygon. The paper also discusses the properties of the moment Newton polygon, including its convexity and the fact that it is a closed subset of the plane. In the Newton polygon np increment kappa, pq associated with equation 8, the slope k of the edge is given by the expression k equals min, npi, pi, q, rqpsn, kappa v, q, r ni l, 1 rlil ni l, 1 ps0 rlil rl lambda psqlx 0 kappa. This expression is derived from the condition S, h, which implies that c ni l, 1 ps0 rlil rl lambda psqlqqq v q arni l 1 rlil acp 0 kappa kappa q for all pi q rqp lambda n and all npi. The tuple pi q rqpsn is chosen such that the edge with slope k is the segment with endpoints ps0 kappa kappa q and ni l 1 ps0 rlil rl lambda psqlqqq v q arni l 1 rlil. This is illustrated in Figure 1, which shows the moment Newton polygon NP increment kappa pq associated with equation 8. The proof of the expression for k involves 2 points. Firstly, the condition S h implies C ni L 1 ps0 rlil rl lambda psqlqqq v q arni L 1 rlil acp 0 kappa kappa q for all pi q rqp lambda n and all npi. Secondly, C ni L 1 ps0 rlil rl lambda psqlqqq v q arni L 1 rlil acp 0 kappa kappa q, which is demonstrated in the figure. The figure is divided into 2 cases: case S h kappa s0 kappa and case S per mil h. In the first case, the edge with slope k is the segment with endpoints ps0 kappa kappa q and ni l 1 ps0 rlil rl lambda psqlqqq v q arni l 1 rlil. In the second case, the edge with slope k is not the segment with endpoints ps0 kappa kappa q and ni l 1 ps0 rlil rl lambda psqlqqq v q arni l 1 rlil. The Gevrey regularity for inhomogeneous nonlinear moment PDEs is characterized by a critical value sigma c, a non-negative real number dependent on the set S. Specifically, sigma c is the smallest positive real number satisfying a specific inequality. This critical value is crucial in establishing inequalities, as presented in proposition 5.6. The proof of this proposition adapts from 22, lemma 3.9, and is divided into 2 cases: when S equals the Hilbert space H, and when S is not equal to H. The derived inequalities play a fundamental role in the proof of the main result, underscoring the significance of sigma c in the Gevrey regularity analysis. By introducing this critical value, the proposition provides a crucial stepping stone in establishing the regularity properties of inhomogeneous nonlinear moment PDEs. The main result of the paper revolves around Theorem 5.7, which concerns the simultaneous Gevrey regularity of solutions to a specific partial differential equation with a power law nonlinearity. This theorem states that for any sigma greater than or equal to the critical value sigma c, both the formal solution RUPT xq and the inhomogeneity RFPT xq are simultaneously sigma Gevrey. The proof involves several steps, including the application of lemmas that establish properties of solutions and inhomogeneities, providing bounds on certain quantities to demonstrate Gevrey regularity. A corollary 5.8, deals with convergent inhomogeneities, where the formal solution is either convergent or 1, k Gevrey, with k representing the smallest positive slope of its associated moment Newton polygon. An example 5.9, illustrates the application of the theorem, focusing on a semilinear regular moment heat equation with a power law nonlinearity. The Gevrey regularity of inhomogeneous nonlinear moment PDEs is discussed through the analysis of the moment Newton polygon associated with equation 12, depicted in Figure 2. The critical value is defined based on the conditions for variables dpt1 nu. Theorem 5.7 establishes the Gevrey regularity of the unique formal solution for equation 12. The discussion is then extended to the generalized regular moment Boussinesq equation 13, in 2 variables pt, xq, where the moment Newton polygon is analyzed, as shown in Figure 3. The critical value for equation 13 is defined differently, and Theorem 5.7 is again employed to establish the Gevrey regularity of its unique formal solution. These findings are crucial for understanding the Gevrey regularity in the context of inhomogeneous nonlinear moment PDEs, providing a foundation for further analysis of these complex equations. The authors present a generalized regular moment Burgers-Korteweg-de Vries equation, a two-variable equation with specific conditions on its coefficients and functions. The moment-Newton polygon associated with this equation is analyzed, providing insights into the behavior of the solution at t=0. The polygon is divided into 5 distinct cases based on the values of S0, Q1's 1, and Q2's 1, which are graphically represented in Figure 4. The first case occurs when Q1's 1 less than S0, resulting in a polygon covering the domain CP Q1's 1, V1Q. The second case has Q2's 1 less than S0, with the polygon covering CP Q2's 1, V2Q. The third case corresponds to S0 less than Q1's 1, Q1 equals Q2, V equals min, V1, V2, spanning both domains CP Q1's 1, V1Q and CP Q2's 1, V2Q. The fourth case is characterized by S0 less than Q2's 1 less than Q1's 1 and 1, V2 Q2's 1 0 greater than equals 1, V1 Q1's 1 0, covering parts of both domains and extending beyond them. Lastly, the fifth case occurs when S0 less than Q2's 1 less than Q1's 1 and 1, V2 Q2's 1 0 less than 1, V1 Q1's 1 0, involving a polygon that spans across both domains but with a different orientation. These cases provide valuable information about the behavior of the solution at t=0 for the GRMBKDV equation, contributing to a deeper understanding of the equation's dynamics and potential applications in various fields. This section of the research paper delves into the Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs. A critical value is identified, which leads to the Gevrey regularity of the unique formal solution. The paper also explores the Gevrey regularity for specific moment Korteweg-de Vries and Burgers equations, providing their respective critical values. The proof of Theorem 5.7, the main result of this section, is presented in 2 parts. The first part employs modified Nagumo norms, a technique of majorant series, and a fixed-point procedure to establish the Gevrey regularity of the formal solution. The second part of the proof utilizes the first point and proposition 6.6 to demonstrate that the formal solution is sigma 1 Gevrey for no sigma 1 less than sigma c, while the remainder function is sigma Gevrey with sigma less than sigma c. The paper also addresses the reciprocal relationship between the Gevrey regularity of the remainder function and the formal solution. By assuming that the remainder function is sigma Gevrey, the authors show that the coefficients of the formal solution satisfy similar inequalities, utilizing an approach similar to that presented in previous sections. This demonstrates the interconnectedness of the Gevrey regularity properties between the remainder function and the formal solution, reinforcing the significance of the critical value sigma c in determining the Gevrey regularity of these inhomogeneous nonlinear moment PDEs. This section of the research paper presents a novel method for estimating solutions to a class of nonlinear partial differential equations. The approach builds upon previous works in the field, such as those presented in 1719 for linear partial and integradifferential equations, 2022 for nonlinear partial differential equations, and 24 for linear moment partial differential equations. The proposed technique utilizes modified Nagumo norms introduced in Section 4 and a technique of majorant series. The authors first derive recurrence relations for the quantities uj, kappa, x, and fj, x, using relations 10 and 11. These recurrence relations are based on the expressions for ar, j, n and I, q, r, j0, x, as defined in the paper. Next, the authors consider the modified Nagumo norm of indices ppj kappa q, alpha, r, square, where alpha is a multi-index with all components equal to p sigma s0, q kappa plus v, and v is the maximum value among v, q, r. This choice ensures that the first value of alpha may be nonpositive, while the second value is always positive, and thus alpha greater than 1. From proposition 4.4, the authors obtain an estimate for uj kappa x pj kappa q alpha r s in terms of fj x pj kappa q alpha r s, which involves a sum over n pi in j, as well as the product of ar j n and I q r j0 x. This estimate is then rewritten in a more explicit form using the expression for pj kappa q alpha in terms of h il x and rl. The paper concludes this section by emphasizing the importance of this new method for estimating solutions to nonlinear partial differential equations, particularly in comparison to existing techniques. The authors also highlight the potential for this approach to be extended to other types of equations and problems in the future. The Gevrey regularity of inhomogeneous nonlinear moment partial differential equations, PDEs, is established through a key inequality that leverages the definition of the Gevrey class and previous assumptions and propositions. This inequality yields an upper bound on the norm of a solution component, a crucial step in demonstrating Gevrey regularity. By applying proposition 4.7 in corollary 4.11, a new expression for the norm of the solution component is derived, consisting of a sum over indices and a product of terms. Each term comprises various factors, including functions related to the initial data, the nonlinearity, and the Gevrey class parameters. A critical term, B1, is identified and bounded by employing the definition of M0 and the properties of the Gevrey class. This term, a sum over indices, involves products of functions related to the initial data and the nonlinearity. The derived upper bound for B1 is essential for completing the proof of Gevrey regularity in subsequent sections. This section presents a pivotal step in establishing the Gevrey regularity of solutions to inhomogeneous nonlinear moment PDEs, introducing a key inequality, applying previous results, and establishing an upper bound on a crucial term, all of which contribute to the overall argument for Gevrey regularity. The moment function M0 and its relationship with the constant C1 are key properties in the development of the research's theoretical framework. An inequality involving M0 and C1 is established, which is then extended to include the variable il. This reasoning is repeated for another variable LPT1, 2. Nu, leading to the introduction of another constant PCL. The inequality is further generalized, resulting in the existence of a constant C2. The passage also explores the properties of gamma p1 sigma ph ilqq and its relationship with the constant C3, utilizing Stirling's formula and assumption 5.3. These mathematical derivations and inequalities are crucial for the development of the research's theoretical framework. On page 25, the authors delve into the Gevrey regularity for inhomogeneous nonlinear moment PDEs. They establish the existence of certain terms, specifically sigma pjv, q, r(rn), which are deduced from previous sections. This leads to the conclusion that the solution to the PDEs satisfies a set of equations, including 17 and 18. These equations involve the use of various constants, such as C3 and C4, which are crucial for the Gevrey regularity. The authors emphasize the significance of these findings, highlighting the importance of these constants and their impact on the solution's regularity. This discussion is dense with technical terms and mathematical concepts, showcasing the author's expertise in the field. In the research paper, we combine equations 15 to 18 to obtain an inequality involving the constant C5, which is used to bound the term B1 in equation 19. This bound is then utilized to derive an inequality for bi, q, r, j, n, which is further used to establish an upper bound for uj kappa, pj kappa q is r, s in equation 20. The bound in equation 20 is expressed in terms of fj, pj kappa q is r, s, which is used to define the modified Nagumo norms. To bound these norms for any j is greater than or equal to 0, we employ the classical majorant series method. In the first step of this method, we define gj, s and alpha I, q, r, j, s, where gj, s represents the product of fj, pj kappa q is R, S and M0 Pj backquote. Kappa Q gamma P1 backquote sigma Pj backquote. Kappa QQ. And alpha I, Q, R, J, S is a constant term. The technical lemma to be proved involves these definitions. The inequality in equation 19 is a crucial intermediate result, as it allows us to establish the bound in equation 20, which is essential for the subsequent application of the majorant series method. The definitions of Gj, S and alpha I, Q, R, J, S set the stage for the proof of the technical lemma, which is a key component of the majorant series method. Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs, is a crucial concept in mathematical analysis. To establish this regularity, the authors introduced two key inequalities involving the coefficients Gj, S and alpha I, Q, R, J, S. These coefficients play a vital role in the analysis of the PDEs. The authors also define a formal power series, Vpxq, with coefficients recursively determined by specific relations. These relations involve the initial conditions and expressions for Vj when j is greater than or equal to 1. A critical proposition is then presented, which establishes the inequalities 22 for all j greater than or equal to 0. This proposition is essential in proving the Gevrey regularity of the solution to the inhomogeneous nonlinear moment PDEs. The inequalities 22 are a fundamental component of this proof, as they provide a bound on the growth of the coefficients Gj, S and alpha I, Q, R, J, S. The Gevrey regularity of the solution is a significant result, as it implies that the solution exhibits a specific type of smoothness. This smoothness is characterized by the Gevrey class, which is a class of functions with a specific growth rate. The proof of the Gevrey regularity relies heavily on the proposition and the inequalities 22, demonstrating the importance of these components in the analysis of inhomogeneous nonlinear moment PDEs. The proof of inequalities 22 is presented using mathematical induction. Assuming the inequalities hold for all k is less than or equal to j, 1, it is shown that they also hold for j equals kappa. The first step is to apply the hypotheses to relations 20, leading to equation 23. This equation is then rearranged to obtain equation 24, where all terms alpha I, Q, R, J0, SVJ1, VJR1 Rn are non-negative. By observing that any tuple Pj0, JR1 Rnq can be seen as a larger tuple Pj0, JR1 Rn, junior 1 Rn 1, JRRQ, where junior 1 Rn 1 equals JRR equals 0. It is shown that the inequalities 0 is less than or equal to alpha I, Q, R, J0, SVJ1, VJR1 Rn is less than or equal to alpha I, Q, R, J0, SVJ1, VJR1 Rn ver 1, Rn hold, using the fact that V0 is greater than or equal to 1. Consequently, the inequalities 0 is less than or equal to n ary summation J0 J1 junior 1 Rn, J Rnl, 1 Rlv, Q, R alpha I, Q, R, J0, SVJ1, VJR1 Rn is less than or equal to n ary summation J0 J1 junior 1 Rn 0 J Rnl, 1 Rlv, Q, R alpha I, Q, R, J0, SVJ1. VJRR is less than or equal to n ary summation J0 J1 JRR, J Rnl, 1 Rlv, Q, R alpha I, Q, R, J0, SVJ1. VJRR hold, since all the terms are non-negative. The convergence of the formal power series Vpxq is demonstrated through its unique solution to a specific functional equation. This equation involves two other formal power series, alpha pec and hpxq, defined using certain coefficients and functions. The convergence of Vpxq is determined using the fixed-point method, where a new formal power series Vpxq is defined as the solution to the given functional equation. The key results include the proof of proposition 6.2, establishing relations between various coefficients, and proposition 6.3, which demonstrates the convergence of the formal series Vpxq. This proposition also provides bounds for the coefficients Vj in terms of two positive constants C1 and K1. In this section, the authors continue their discussion on the proof of the first point of theorem 5.7, focusing on bounding the modified Nagumo norms using previously established propositions 6.2 and 6.3. They introduce the concept of a series Vpxq, defined as a sum of terms involving the variables x, micro, and rc micro, rr, which are generalized Catalan numbers. The series is shown to be normally convergent on a specific disk with center 0 pc and radius, implying Vpxq is analytic at 0 pc, thus completing the proof of proposition 6.3. The authors then use this proposition along with proposition 6.2 to derive corollary 6.4, which provides an upper bound for the modified Nagumo norms in terms of the parameters C1, K1, and the gamma function gamma p1 sigma jq. This bound is essential for establishing the first point of theorem 5.7. The paper also highlights the significance of generalized Catalan numbers, which appear in various areas of mathematics and computer science. Overall, this section contributes to the overall goal of the paper by providing a detailed analysis of the convergence properties of certain power series and their relationship with modified Nagumo norms. The authors provide a proof for the fourth step of Gevrey regularity for inhomogeneous nonlinear moment partial differential equations. By applying proposition 4.13, they obtain a crucial estimate on the subnorm of the solution components Uj, essential for establishing Gevrey regularity. This ultimately leads to the conclusion that the second point of theorem 5.7 holds. To further analyze the Gevrey order of the formal solution rupt, xq, the authors introduce an auxiliary function emp, x. This function is defined as a sum of products involving the moment functions mdpj and their derivatives. They then prove that emp, x, is an analytic function on a specific polydisk. The ultimate goal is to demonstrate that the formal solution rupt, xq is generically sigma c Gevrey and cannot be better than sigma c Gevrey. This is a critical finding, as it sheds light on the regularity of solutions to inhomogeneous nonlinear moment PDEs. The author's approach, leveraging proposition 4.13 and the auxiliary function emp, x, provides a rigorous framework for understanding the Gevrey regularity of these solutions. In proposition 6.6, the authors establish the sigma c Gevrey property of the formal solution to equation 26, a nonlinear partial differential equation with inhomogeneity RFPT, xq and initial conditions phi jpxq for j equals 0, kappa 1. The coefficients I, q, r are positive real numbers, and the initial conditions satisfy certain analyticity and boundedness conditions. The proposition asserts that if the inhomogeneity RFPT, xq is sigma Gevrey and satisfies certain boundedness conditions, then the formal solution rupt, xq is exactly sigma c Gevrey. The authors note that equation 26 can be reduced to a simpler nonlinear equation, but they choose to retain the original notation for clarity. The proof of proposition 6.6 involves rewriting the general relations 10 as identities, which are used to establish the sigma 1 Gevrey property of rupt, xq for no sigma 1 less than sigma c. Specifically, the authors rewrite the relations as uj kappa, pec, I, q, rpex m0 pjq m0 pjv, q, rqbq nm, zujv, q, r in, pec rjpxq, where uj kappa, pec is a solution component, I, q, rpec is an analytic function, and m0 pjv, q, rq is a bounded term. The authors leverage D'Alembert's rule to establish the convergence of the series n-ary summation J0, x, j, which is crucial for the proof. The proposition and its proof provide a significant contribution to the understanding of the sigma C Gevrey property of solutions to nonlinear partial differential equations. In the context of inhomogeneous nonlinear moment partial differential equations, PDEs, the Gevrey regularity plays a crucial role. To establish this regularity, we first define the coefficients I, Q, R and the initial conditions phi j p x q, as well as the inhomogeneity RFPT, xq. By applying these definitions, we can show that the solution Uj, Pec satisfies a set of equations, which involves imposing hypotheses on the coefficients and initial conditions, as well as the inhomogeneity. Specifically, the coefficients I, Q, R are assumed to be smooth and bounded, while the initial conditions phi j p x q are required to satisfy certain regularity conditions. The inhomogeneity RFPT, xq is also assumed to be smooth and bounded. By leveraging these assumptions, we can derive a system of equations that the solution Uj, Pec must satisfy. The Gevrey regularity is then established by demonstrating that the solution Uj, Pec possesses a certain level of smoothness and decay, characterized by the Gevrey class. This regularity result has significant implications for the study of inhomogeneous nonlinear moment PDEs, as it provides a framework for understanding the behavior of solutions to these equations. Notably, the present analysis relies on a set of hypotheses on the coefficients, initial conditions, and inhomogeneity, which are crucial for establishing the Gevrey regularity. Future work may involve relaxing these hypotheses or exploring alternative approaches to establish regularity results for inhomogeneous nonlinear moment PDEs. The authors present a proof for proposition 6.6, relying on lemma 6.8, which states that for any integer $, GEQ $0 and $j, GEQ $1, the inequality $j, 1 zk, 0 vis L, 1 pkpv aq lik $, holds. This lemma is proven by induction on $j, with the base case $j equals $1 being trivial. The induction step involves showing that if the inequality holds for some $j, GEQ $1, then it also holds for $j plus $1, achieved by applying the induction hypothesis and rearranging terms. Utilizing lemma 6.8, the authors deduce the existence of two positive constants $c, k, GEQ $0 that satisfy equation $27, $ujpli, q, r kappa, I nq in, p0 kekjpjv, q, rq, s0 ens d, 1 pjqn, dq, sd Furthermore, if $rupt, xq is sigma underscore $1 Gevrey for some sigma underscore 1 less than sigma underscore c then definition 3.1, properties of moment functions, and inequality $27 imply equation $28 $1 dc 1 k1 j gamma p1 p sigma 1 plus s0 qpjv q r kappa I nq pjv q rq s0 ens d 1 pjqn dq sd for all $j, GEQ $0. This leads to a contradiction, as the right-hand side of $28 tends to 0 as $j tends to infinity, which is impossible according to Stirling's formula and the definition of sigma underscore c definition 5.5. This concludes the proof of proposition 6.6. Gevrey regularity for inhomogeneous nonlinear moment partial differential equations, PDEs, is a crucial concept in this research. The significance of this result stems from the choice of moment functions and the application of theorem 5.7. The authors contrast their result with the Cauchy-Kovalevskaya theorem, noting that their finding is weaker in the Kovalevskaya case due to the chosen Newton polygon and calculation method. This distinction is essential in understanding the limitations of the Gevrey regularity result. The Cauchy-Kovalevskaya theorem, a fundamental tool in PDE analysis, guarantees the existence and uniqueness of solutions to certain PDEs. However, the theorem's applicability is restricted by the Newton polygon, which affects the Gevrey order of the formal solution. The author's approach, while providing valuable insights, falls short of achieving the optimal Gevrey order. Future research directions are proposed to improve the Gevrey order of the formal solution, with potential applications in various fields where moment PDEs are employed. The discussion builds upon previous pages, offering a comprehensive understanding of the research and its implications for the study of inhomogeneous nonlinear moment PDEs. The authors present a comprehensive list of key findings and implications from their study on the impact of climate change on marine biodiversity. They highlight the significant decline in species diversity and abundance, as well as shifts in species distribution and migration patterns. The study also emphasizes the increased frequency and severity of extreme weather events, which further exacerbate the effects of climate change on marine ecosystems. The authors discuss various factors contributing to these changes, including rising sea temperatures, acidification, and changes in oceanic conditions. They also emphasize the importance of addressing these issues through conservation efforts, such as protecting vulnerable habitats and implementing sustainable fishing practices. Moreover, the authors stress the need for continued research into the effects of climate change on marine biodiversity, particularly in terms of its socio-economic impacts and potential solutions. They suggest that a multidisciplinary approach involving scientists, policymakers, and local communities is essential for effective conservation strategies. The study concludes by emphasizing the urgency of addressing climate change to preserve marine biodiversity and mitigate its far-reaching consequences. It calls for immediate action to protect our planet's marine ecosystems, which are critical components of the global ecosystem.